second half of chapter 3 gets into these ideas of what's going on with graphs of polynomials, factoring them, finding zeros, sometimes called horizontal intercepts, both real, complex, and imaginary, or I should say all real, and then we'll look really quick, a little bit at the end on rational, inverse, and radical functions. So this is an equation along with its corresponding graph. So, and it's already factored out. If it had been written out completely, we'd be talking about something that, so this would be x cubed, this would be x squared, and then an x, so I'd have 3, 4, 5, 6. It would be an x to the 6th function as the highest power, so it'd be a 6th degree polynomial. That's what it'd be called, because the highest power is 6. But looking at the equation, and how does that correspond to what's going on with the graph? If we look at these, and they're written as binomials and then lowest to highest power. And that's the standard form for how you want to do it. We try our best to have things, when we do it as a polynomial, highest to lowest power. This way we go lowest to highest. And honestly, it doesn't really matter. It's just a common practice. But this one right here, x plus 3, when looking for horizontal asymptotes, another word for horizontal asymptotes is a 0. That is, where does this equation equal 0? Which means either this has to be 0, this has to be 0, or this has to be 0. And the three places that the whole function equals 0, well, when is this 0? It's 0 at -3, which is right there. Where is this 0? Well, that's at 2, because 2 minus 2 is 0, and that's right there. Where is this one 0? It's at -1, because -1 plus 1 is 0. And then, again, so 0 times anything is always 0. So that would happen right here. And we have 3 different things going on at those 3 different zeros, or horizontal asymptotes, because it's the horizontal axis, sometimes called x-intercepts, horizontal intercepts, zeros, and also roots. Use those all interchangeably, only why? Because we want to make it confusing. That's what we do as mathematicians. But if we look at x plus 3, this by itself, because there's no power on it other than 1, this is a linear function. How do linear functions operate? They operate kind of like as a straight line. And that means that when this graph crosses at 3, it's crossing similar to the way a straight line would. Granted, it's not actually a straight line, but it is like a straight line in how it crosses the axis. Then we have here at 2, and this part here is squared, so that's a quadratic function. Quadratics are like parabolas. All right, so how the graph is looking and functioning at this point, at point 2, kind of is parabolic. It's coming down and going up. Again, not an actual parabola, but it is demonstrating some parabolic tendencies. Now, if my leading coefficient was negative, we'd be talking about one that goes down. All right, and then here at 1, or at -1, that is, we're trying to figure out, okay, where is this happening? What's going on here? Well, this is a cubic function. And a cubic function is like this. And if you don't recall a cubic function, that's kind of how it goes. It will go like that. If this one happens to cross on the x-axis. So when we're looking at this graph, that's kind of how it's looking at that point. It's the cubic part. And then the last thing we can do is we actually can find the vertical axes intercepts. Like, where does it intersect the vertical axis, the y-axis? All right. And what happens there is when all of these get multiplied out, the last thing in each of these binomials, so I've got the 3, which is just raised to 1 power and is a positive 3, so I leave it as a positive 3. And then I have the -2 right here, but it's squared. So when we're doing this, it'll be x minus 2 times x minus 2, so you'd FOIL that out. It'd be -2 times -2, which is positive 4. And then the last one cubed, it's going to be 1 times 1 times 1 when it gets fully multiplied out, and that's 1, and those add up to 10, and that is the spot right there where it crosses the y-axis. So then if I have an equation like this, we could say, well, hypothetically, what might this look like? Well, the roots that I have in this here, I have x equals -4 is one of the roots right here. I have x equals -2. I have x equals +1. and I have x equals 3. So I would look and say, well, let's start making an equation for that. So x equals -4 means x, so I'm going to have f of x equals, I'll have x plus 4 in parentheses. Why x plus 4? Because if -4 is 0, it makes it 0. X plus 4 is the actual factor. All right, it's operating like a straight line, so I leave it as a straight line, so just 1 power of 1. What's happening at -2? So then that'd be x plus 2, because -2 makes it 0. Also operating kind of like a straight line. I have my function at +1, so this will be x minus 1, because when you put 1 in there, it makes it 0. There it's kind of looking parabolic, so that would be squared. And then finally at x minus 3, and that is a cubed function, so then that would be cubed, but it's also going down, so it's going to be a negative value here. So as we're looking at then how all this works, the last thing would be my y-intercept is at +1. So what I would do is I would take a look at all of the things going on here. I got a 4, a 2, a -1 squared, so that's a +1. So I've got 4, 5, 6, 7. And then I have -3 cubed. So 7 minus 27 is -20. But I need to be +1. So I'm going to add 21 at the end. And that will get me back to, so this will be one way to possibly demonstrate a function similar to what we have graphed here. And how you look at a graph, you can get a ballpark idea of what the equation might look like, and vice versa. So is -3 a 0 of that function? Essentially, if you put in -3, will my function equal 0? It's a simple matter of just plugging it in and finding it out. We could also see if x plus 3 divides into 2x cubed minus 7x plus 3. All right. To do that, now would then just like we do in long division, how many times does x go into 2x cubed? And the answer, it goes in there 2x squared times. Oh, but if you look at my original function doesn't have a squared. So I'm going to rewrite it as plus 0x squared, then minus 7x plus 3. So I keep everything lined up, and I have all of my variables and exponents going in descending order, and I'm not missing any. So then I multiply 2x squared times x plus 3, 2x squared times x, and then 2x squared times 3. And then it would be, so that would be 2x cubed plus 6, what's a 6? X squared. Like we do in division, we subtract. This is 0. This is -6x squared. We bring down the next term, which is -7x. And we look again and say how many x's go into -6x squared, and the answer is sorry, stay with red here, -6x. And so when I multiply that, I will then get -6x squared and -18x. And then we subtract, so negative minus negative, that's 0, -7x minus a -8, and that's 18x, by the way. Minus a negative is plus a positive, so that's positive 11x. Bring down the 3. And then my last item up here will be positive 11. And when I multiply that through, I'll have 11x plus 33, subtract. Lo and behold, it does not subtract to 0. Therefore, x plus 3 is not a root, which means -3 is not a 0. Synthetic division is a similar idea to long division, but because mathematicians, we tend to be on the lazy side of things, we're always looking for ways to simplify, streamline, abbreviate, etc. So let's take a look at synthetic division. Start by taking the first number that's there. So the numbers here that I have, 1, 4, -5, -14, correspond to the coefficients of all the terms in descending order. And there's a cubed, squared, single, and then x to the 0, which is just 1, which is why I just have the constant -14. If I were missing one, let's say I was missing this one, I would actually have to put 0 down here for this. You don't want to forget any of them. But anyways, we take that first item and all we do is we just bring it down. And that's where we start. We start with the 1. All right, and then we say, okay, now we take the 2 from the divisor and we multiply it by the 1 that we just brought down to get 2, and that goes here as 2. And then we add that to get 6. And then we take that 2 as the divisor again, times the 6. Times the 6 then, right here, 2 times the 6 to give me 12. And then add them down. Gives me 7. Then 2 times the 7 going up, that's 14. Add it down, that's 0. So 2 is a 0, which means x minus 2 is a divisor. And then it would be factored into x squared plus 6x plus 7 as the polynomial then that's the result of doing the squaring. Which will give me 7. Don't know why there were already 2 seconds on here. My apologies if something's going glitchy on the tech. Cauchy's bound. So for any function, and this is the generic form for any function. So my first term, so my first constant a to the n, and my x to the n. So if I had a 6th degree polynomial, this would be a sub 6, which is my 6th coefficient, to correspond with the x to the 6th power. All the way down to my last coefficient, which is x to the 0 power. And x to the 0 power, we typically don't write at all. We just leave that off and we just say a to the 0. Sometimes you'll see x to the 0 there as well, but that's what that means. So that's my constant term. But here's what it means, is if I take m, and m is the largest coefficient of all these a's, I pick the largest one, and I take the absolute value of it. So just whatever it is, it's a positive number. So if this number here was a 12, and that's the highest number, then m is 12 and m is 12. If that was a negative 12, it would be 12 and it would be 12. And then I take this value, take its absolute value, put that in the denominator, and then I take the negative of that fraction, minus 1, and then I take the largest coefficient divided by that first thing there, and then add 1. And what that means is if there's going to be a 0, it will occur somewhere in that interval. Let's take a look at one. So in here, we have the original function, 3x squared plus da, 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 da. Here it is. And we're going to use that formula. So m is the largest coefficient, which is negative 12, but we take the absolute value, so it's just 12. A sub n, which is the leading coefficient, that's 3. So I take 12 over absolute value of 3, which is 4. Make it negative, so negative 4 minus 1, that's negative 5. And then I take Cauchy's, the upper bound. M is 12 divided by 3. It's the positive version of it. And then plus 1, so it's positive 5, which means if there's going to be a root to this, it's going to be in this interval. And then we take it a step further and say, okay, now what can my rational zeros actually be? What can my rational zeros be? We're going to look at that and say, all right, well, they are of this, they can be any, if they're going to be a rational zero, so a rational zero, which means it's just like a number, a whole number, or a fraction, not a square root. Square roots would be irrational zeros. They still exist, they're just called irrational. But if it's going to be a real zero, it's going to be in a fraction like this, where p are all the factors of a sub 0, which is the last term, and then q are all the factors of a sub n. So when we look at this, we say, okay, all the factors of 8. So that would be 8, 4, 2, and 1. And then all the factors of a sub n, which is 3, will be 3 and 1. So when I'm thinking of all the possible roots, it's going to be plus or minus 8 over 3, plus or minus 8 over 1, which is just 8. All right, because again, I'm taking P over Q, so P over Q, and then P over Q. And it's plus or minus, which means it could be positive 8 or negative 8. Positive 8/3 or negative 8/3. And then just keep on going down, plus or minus 4/3, plus or minus 4, plus or minus 2/3, plus or minus 2, plus or minus 1/3, and I ran out of room, plus or minus 1. If there's going to be a rational 0, it's one of those. Doesn't mean they all are, just means if there's going to be one, it's one of those. And then you do the same process of synthetic division to start working your way through. But remember, Cauchy's sets a boundary and says if they're going to happen, it's going to be in that interval. And then here, back to the quadratic formula, which we've looked at. I think I had on a previous video as well. We'll just kind of run through this here quick in case you haven't done it in a while. So x equals negative b. So b is negative 2a, b, c. A is the x squared term, b is the x term, and c is the constant. So it's negative 2 already, so now it's positive 2 plus or minus the square root of b squared. Negative 2 squared is positive 4. Be careful, calculators will sometimes tell you it's negative 4, and that's wrong. Minus 4 times a, which is 1, times c, which is 5, all over 2 times positive 1. I'll have 2 plus or minus the square root of 4 minus 20 divided by 2. And now you might start be thinking, what's going on here? Because I'm going to have 2 plus or minus the square root of negative 16 divided by 2. And in the past, you've said there's no way you cannot take square roots of negative numbers. In the real number system, you are correct. But in this case, it's imaginary. You might be thinking, but does that really exist? The answer is yes, it does. Imaginary numbers do exist. We call them imaginary, though, because we used to call the other ones real. Well, if they're not real, then they're imaginary. But what I end up with is I have 2 plus or minus the square root of 16 times the square root of negative 1. I can split that up, divided by 2, and then that would be 2 plus or minus 4. Square root of 16 is 4. And the square root of negative 1 is its own special thing. It is equal to the letter I. So I'll have 4i divided by 2. I then reduce 1 plus or minus 2i. And this would be 2 imaginary roots when I would graph this quadratic function. So the quadratic function itself never crosses the x-axis. So it's going to be either a parabola up that's above the x-axis, or in this case it would be above because it's a positive coefficient a is 1. It just never crosses the x-axis. It still has 2 roots. It's just that the roots exist in the imaginary number system, not in the real number system. Rational functions here, kind of run through what this is. Rational means some in the numerator, some in the denominator, but we don't have square roots. So if I have this function here, first I look and see that nothing is identical top and bottom, so nothing can be reduced. As I think about how to graph this, I want to find out where does my equation, what happens at f at 0. All right, so on the x and y axis, if I were to draw this in, I'd be talking about the y-intercept. And the y-intercept happens when x is 0. So when x is 0, plug in 0 to that equation. 0 minus 2, so negative 2. 0 plus 3 is 3. Negative 1, 2. Negative 5 gives me this, which means my graph will intersect the y-axis right there at 0, comma. It's in the denominator. Sorry, it's below the axis. 0, comma, negative 3/5. All right, and then I look to the equation and say, where is the equation equals 0? That is, where does this all equal 0? Well, that's when x is 2, because 2 minus 2 is 0, or negative 3, because negative 3 plus 3 is 0. So my two zeros are x equals 2 and x equals negative 3. So down here at negative 3 and up here at positive 2 is where it will cross the axis. I have all leading coefficients, which means I'm going to have I'll just carry on. And then discontinuity. Discontinuity means where is my graph not? Horizontal intercepts are also called the zeros. Where is my function not function? My function does not function at x equals 1, because if I look in the denominator, when x is 1, I get 0. 0 times anything is 0. And you cannot have 0 in the denominator, which means I have either a point of discontinuity or an asymptote. All right, so I'll have something at x equals 1, x equals -2, and x equals 5. So what does that mean on the graph? That means that over here at 5, I have a horizontal line or a vertical line that's dashed. At -2, there's a vertical line that's dashed. And at +1, there's a vertical line that's dashed, which means my function will be somewhere over here and crosses the axis. It'll be somewhere in here and crosses this axis, but doesn't cross the x-axis, so it probably goes up and down, something like that. It'll be in here and will somehow cross the axis, but it'll either go up or down. And then we'll be somewhere out here and neither cross the axis because I don't have any zeros out there because I only have 2 zeros. So if something's going to happen way out here when x is really, really, really large, it'll cross the axis and do something out here. But that gets you an idea of at least a beginning place for sketching out graphs. All right, this is a irrational function, right? Or a radical function. Radical because there's a square root. Square roots are sometimes called radicals. Amongst the more mathematically articulate and higher, if they want you to use more math language, we're going to say that it's a radical function, not a root function. All right, but within this is the equation for velocity of a car slamming on its brakes. And you can work it backwards. So if you know things like the length of the skid marks, the coefficient of friction, which is going to be different for every type of tire. Some have better friction constants than others. The greater the constant means the stickier it is, so to speak. And then G is gravity, because that's going to be true for all vehicles. And if we know those 3 pieces of information, we can determine what the original velocity was of some car. So if I had a car that created a 200-foot skid and had a certain brand tire with a coefficient of friction of 0.35 and gravity, we know this is a constant, 32 feet per second. We plug those into my equation, and I have the original velocity given the distance is equal to 2 times 32 times 0.35 times 200. And it's just a matter of plugging that in your calculator to find out what your original velocity was. And that would be in feet per second. All right, and which many people don't think feet per second, so you'd have to do some quick conversions to make it into miles per hour. But that would be what would be considered a radical function that we're graphing. Oh, and then with that as well, with that radical function, there are some domain restrictions. You cannot have a length of a skid mark that's a negative number, because then this would be negative underneath, and then there would be imaginary, but it also doesn't make sense. You can't have negative skid lengths. Gravity can only be written as a positive. Gravity, when we're doing other equations, we'll be talking about the fact that it's pulling things down, which means it's moving in a negative direction, but don't worry about that. And coefficient of friction is always a positive number. If it were less than 0, that would mean there is less than no friction, and you can't have less than no friction. The least amount of friction you can have is none, which is near impossible to get anyways. And less than no friction would be imaginary. So that would be a case where we can't do imaginary. And then inverse functions, you probably had looked at them long time ago in your math career. It's when we take any function and reflect it over the y equals x line. So in a graph, if I have the line y equals x, it goes like this. And if I took my function and reflected it over that line, or pretend like you folded it over this line here, fold the graph over and trace it, that would be what it is. Algebraically, inverse functions are take the x and the y and switch them and then solve for y. So subtract 1 from both sides. And then I need to get rid of the square, and the inverse operation of squaring is square rooting. And since I had something that was squared and square rooted, that means anything for y, if it's positive or negative, works because it gets squared first. So negative squared is squared, and then take the square root, it's also positive. So what I would have is y will equal plus or minus the square root of x minus 1. All right. So y equals x squared plus 1 is a parabola. If you were just to graph this in a graphing calculator or on something like Desmos, if you're not familiar with Desmos, desmos.com. It's an online graphing tool. If you don't have a graphing calculator, it works really, really well. But if you were to only graph this, it would give you something that looks like a half of a parabola. Like that laying on its side as opposed to a full parabola. Like this. So it gets reflected and it goes over like that. That's an inverse function. Boy, that's a lot of talking for me today. I apologize again, there were some tech glitches that happened mid-cycle. You'll be able to figure that out and go through it. There you go, chapter 3 in a really, really big nutshell.